So thank you for this opportunity. So thanks for everyone for coming. So I am from CSIRO and working in bushfire behavior research activity. Yeah, okay. Yeah. So I will try to be quick. So just outline what is CSIRO, what we are doing, and then more focus on bushfire behavior research lab in CSIRO, and then our current projects, and firebrand tracking is my project. So try. Yeah, okay. Yeah, now it's good. So CSIRO is Commonwealth Scientific and Industrial Research Organization, and we are one of the world's largest disciplinary projects, and they have more than 6,000 researchers across the country and overseas. And there are more than 10 research units: space and astronomy, mineral resources, health and biosecurity. Our environment is our department, and energy and manufacturing, and egg and food. So our strategy in CSIRO is try to solve some environmental problems or more common problems to society, and that having more effect on people themselves. And then our vision is to create a better future for Australia, and not especially Australia, but globally it would be very good as well. So then our National Bushfire Research Lab. So it's home to CSIRO Bushfire Behavior and Suppression Team, because previously the wind tunnel was in other place, and then the office was in different places, so they have to move. Now they put them all together, so have our offices inside. And then 2 wind tunnels. One is Baratron, is a combustion wind tunnel. This is a horizontal one, and a vertical wind tunnel is another wind tunnel that I'm working on it. And this is our team. So Andrew Sullivan is a team leader. He has 35 years experience of bushfire. And Matt Rashki is 15 to 20 years experience. Marek Toy is a visiting scientist from Czech Republic, and he was here just 2 years, and he just left last month. Mark is our technician, and me just started 2 years ago. And Miguel is more than 25 years experience in modeling and bushfire modeling. And so Baratron wind tunnel combustion, it's a 29 meter long with 2 meter by 2 meter cross section. So it's a very big one, and have a 7.2 meter long test section with 1.5 meter wide. So you can put all the fuel types here. And the run speed, it can be up to 5 meters per second, which is equivalent to 55 kilometers per hour above canopy. And it's an automated fan control and data acquisition. We have some sort of sensors like RH and T, barometric pressure, airspeed, thermocouples, and some cameras. And this is a vertical wind tunnel. So it just is designed for study of aerodynamics and combustion of firebrands at terminal velocities. It's 11 meter tall with 4 meter working section, and it's operating over 2 floors, and it can be run to up to 20 meters per second. And the tapered working section is 1.51 angle, just to make sure that, because while burning the firebrand, it reduces its terminal velocity, so it will goes up. So we try to reduce the speed while going up to try to keep it in 1 meter area to track it. So working projects now, the largest one now is trying to link the wildland fire compatibility itself with emission factors, biochemistry, and fire behavior using spectroscopy. So it was just in the phase 1. We just want to know how we can link those together. So we put spectroscopy in our horizontal wind tunnel, and we can do scans pre and after burn. And while we burn it at different fuel moisture contents and 3 fuel types, just to see if this spectra can give us some correlations between the different fire moistures, and can it detect it or not. and then also greenhouse gas emissions and biochemistry. And if you want more about these projects, we can talk later about this. Another project is with Matt. So we just provide a comprehensive understanding of how an effective of wildfly, and this is different aircraft are used. So in Australia, they use lots of different aircraft to suppress the fire, and they want to know which is the effective one, overall effectiveness, what is the best one for different categories or different fires, and even the effectiveness of the drops and how it will be affecting the fire suppression. So you can see here even this one is continued even after the drop of the fire, of the water, and some retardant, and we want to see the effect of retardant as well. Another one is with Miguel. He just want to make some modeling of fire spread. So we started with a very small paper work from 1960 until we have this spark. It's all automated last year. And then it's trying to improving, but as we said, like Alex and all this, it's very hard to put some spotting in Spark or in any fire behavior models because all the numbers are arbitrary now, and they use simplified firebrand sizes, shapes, and fixed numbers, which is not quite accurate. So the last project is my project. We are working in firebrand aerodynamics and combustion. So in our vertical wind tunnel, we just want to know how the firebrand itself in the bloom of air, or similar to bloom of air, how it's burned, and we know the long time with different firebrands, different sizes, different shapes, what is the aerodynamics effect, and how long it will burn for, and we want to track its movement and its aerodynamics. So for example, this burn, it was in this direction, and then suddenly, because of the wind change, the flank becomes the head fire, and it moves all the way. And I think this is in Victoria, and this is the spotting, King Lake, and you can see now all these spotting behaviors. Most of them are short distance, but you can see all these spots here, and even from the other side, how it's affecting the houses and all this stuff. So all this small area burning is spotting, and even it crosses the barriers to the different side of the road, as you can see here. So we'll skip the spot fire definition because lots of people talking about it. So it's just 3 phases of generation and transport, and it's more critical because it just breaking the natural barriers and also starts the fire in a different location, which is very hard to control. So it's a better understanding of this aerodynamics and combustion will lead to improve our prediction, and also we try to communicate with people to make the communication with them how to evacuate and all this stuff, like because of some summers, like in Black Summer, as Alex said, it turns to 30 kilometers away, which is unexpected, and some people were not very careful about these things, and suddenly they find a fire in their homes. So there's lots of parameters affecting the spotting, from bark ejection height, bark size, and velocity and angle, and temperature and moisture content, and direction and speed. But in the vertical wind tunnel, you can only study those first 4, so how far it goes, and then with some other models you can see effect of the wind and how long it will burn. So we have the dynamic combustion, aerodynamics interaction, transport prediction, realistic morphology, flow and burning conditions, and model validation with experiments. So because we are lacking this model validation, in all our models we put spotting as a numbers. We want to try to make some experimental data for them to be able to validate their model. So this is a vertical wind tunnel in details. We start with a centrifugal blower and then diffuser section. And we have screens to make the airflow streamed and uniform. And then we have the turning section and the straightening again to reduce the turbulence intensity. And then the contractor to increase the speed again. And all these are fixed, you cannot change it. So you only can play with adapter and put perforated aluminum screen to change the airflow conditions, and the working section itself, that where most of the fun happens. So in my postdoc, we upgraded the wind tunnel to be fully automated, so you can control the speed. We just, previously it was manually, and now we make it all automated. And we developed a code for controlling and reading all the sensors, like temperature and RNH inside the test section and outside in the environment. And we started with flow modification, because previously all the firebrands will, when we put it in the wind tunnel, it stick to the wall. And why is this? Because of the boundary layer effect, and it have lower speed at the wall, and then you always have the firebrand stick to the wall and it's burning stick to the wall. So we try to avoid this. So we make a jet flow in the corners to make the stream, or to reduce the effect of boundary layer. You cannot eliminate it, but we make an area that will have a higher speed. So whenever the firebrand want to attach the wall, it will go back to the center where we have most of our experiments. And then we make a full characterization with pitot tube, different levels of hertz, which is a fan hertz, which is RPM. And then we have the full map. So now, if you put the firebrand inside the wind tunnel and you run the speed, you know exactly the vertical velocity, which is equivalent to the terminal velocity of the firebrand itself, if it's stable. And then this is our MATLAB modeling. So we burn the firebrand, or even without burning, and then we try to track all the movement inside. So we used 3 orthogonal cameras to track the particles of firebrand. And then there's lots of challenges, because most of the tracking algorithms are working on if you have fixed shape, it's much easier, because the algorithm will know this shape and it'll track it. If it have fixed color, you can also make this tracking. But with burning firebrands, it's very hard, because it loses its shape and color because of the flames and all smoke and all this stuff. So we tried a lot to do this spark trajectory algorithm with MATLAB, and we finally make it with these 3 cameras that they are synchronized together from different angles, and then you can get or build your own 3G trajectory. And you can see that it have different colors, which is this velocity magnitude from lower to higher, and then this is the time scale. So at every second you have the time, so you can know exactly like how long it will burn. And this is just a short video. And some of them burn for 4 minutes, 5 minutes, which is, you will find a very complicated shape, and we want to study this. Another thing is burning phase. So before any adjustment, it's just HSV, and you transfer the RGB to HSV, and then you can see different combustion phases. So flaming, it will be adjusted in this area only, and then glowing and smoldering. So basically, you know how long it's burn, how long it will be flaming and glowing, and then you have just box plot for this one, and you can see the phases. And this is just a burnout, and once it burn out for 5 seconds or more, you know it's now not danger anymore. Then we move to machine learning. So instead of making with MATLAB, we try to label all these burns. We have 12,000 frame that we give it to the learning algorithm, and then he can detect the bark in the 3 different cameras. And which much easier, and also he can solve some problems that we're facing in the algorithm of the reflection from the windows, which is harder to do with MATLAB, that you make it more specific, but with machine learning it's more applicable to any other firebrands or even different projects. If we have another collaboration that we want to use the hailstorm and see how it will affect. So different from fire to ice. And then you can calculate the trajectory as well, as you said, and the vertical or horizontal velocity, and you see how it flips, how it rotates. So if it's very long firebrand and with aspect ratio is long, it will try to dive a lot. But if the aspect ratio is almost 1 to 2, it will do this helicopter shape. So you can see all this effect in the velocity magnitudes. And the last improvement now, we are moving to stereo cameras. So stereo cameras is much better than the orthogonal cameras. It gives you the mapping function and depth from one camera because it has two lenses similar to the eye itself. So with one camera you can detect the particle velocity acceleration in the three different positions, which is more accurate and less computational time. But we are still trying to improve these stereo cameras and we get a higher resolution one. So this is a future work. We will set some burning bark videos for large data sets. We will try to make machine learning for labeling and make the data available for everyone so they can use it with the satellites and everything for labeling and annotation. So we want to do different types of barks, mesmate, gum trees. As Leek said, some of the candle bark, if it's flat surface and if it's curved, the curved one is most dangerous, and this is the one that it traveled 30 kilometers because it contains the fire inside the curved, and even if it's very high condition with wind speed, 100 kilometers per hour, it's still flaming from inside because it's protected. So that's why when it's translated to another location, it's still burning and it can do the spot fire. So we want to do lots of data sets with different firebrands, different sizes to see how it affects. And then this is our page, and we try to. Thanks for everyone, and if you want to contact us, and thank you.